Okay, thank you very much. It's a great. It's great to have me. It's my great honor to speak at this wonderful workshop, and this is actually my first time to speak at a high-energy pheno-driven workshop. I hope it's not the last time. Let me ask you one question to make sure everyone follow. So, how many light color chessmen here on the screen? How many? Quick. 16. Very good. 16. So, how many dark color? Quick. Very good. So this will be some kind of key cartoon you should remember, and we will later to relate this to some chiral sector standard model, called light sector nearly massless, and also some mirror dark sector massive gap sectors. And we will also question how many biofermions actually there are per generations, and also in total in the standard model. This is work done with Yuta Hamada, so Juven Wang and Yu, and thanks for their brilliant collaborations. Oh, by the way, this slide is downloadable here, and if you want to, I'll also put on my website later. So two crucial tools in our work, distinct from the many interesting works in the workshop, is that we kind of question what is mass and how to give a mass. And we use a lot of conventional mechanisms that you cover Higgs confinement, as you just heard from Jessica, but there could be more mechanisms beyond that. Especially driven by interaction, not by mean field. Okay. The second tool is that we use other than anomalies, particularly local anomalies captured by Feynman graph. There is also non-particular global anomalies, and we use that a lot in our work. And the cancellation of them I mentioned is very important. We use that to predict beyond standard model sector. It's very constrained. And to go a bit more is that the mass actually should be just some energy eigenvalue of a quantum Hamiltonian theory system. And diagonalize the Hamiltonian phi eigenvalue, the first and ground state has some energy gap, a finite gap, at some log size system. In the relativistic system, you can look at dispersion above the energy gap in the interacting system. The dispersion will go like this, but generically, this dispersion for this and that may not have a direct relation for non-relativistic system. But we will define an energy gap and mass gap by this relation. And secondly, you can look at correlation function between some matter field. And this will be exponential decay, signature correlation length, inverse of mass. So this will generally work to define mass. So this will not be just the mean field mass adding to Lagrangian. It could be some non-mean field mass, and it could be some terms that you add with highly multi-fermion interactions, some new matter field interact, and then the condensate of that may be zero. Even the 2-point correlation function for different fermion maybe zero, but energy gap can still be non-zero. Okay, so these will be the main tools. Whenever you see later in my talk, you should always go back. We are using these tools. And there are 3 messages I want to convey very quick. One is about neutrino, another about quantum phase transition at 0 temperature, not thermal, 0 temperature. Yes, and the third one is about strong CPU problem, some possible new solution. The first one is that neutrino actually carry anomaly index, just like one of the chessmen actually carry some index, and they are important to cancel some anomaly. But we are looking at some global anomaly, which is a Z-system class. We question their existence, and it can be replaced possibly by other sector. We don't observe the right neutrino. One possibility is the gap TQFT sectors in 4D or gap 5D theory, short dimension, or 4D gapless CFT. Okay, and then you need to ask how to give mass. Once the right-hand neutrino is removed, the hand neutrino give mass in some way, so there could be different mass mechanisms. And the second one is something related to beyond Landau-Ginzburg type of phase transitions. The gradient by theory can be looked at just what David talked to you yesterday about this symmetry breaking type of Landau-Ginzburg phases. But between them, there could be some global anomaly Z2 class control the phase diagram. And I'll mention there are some deconfined groups that show up. You will see that there are natural some BSM, dark gauge, and new matter field show up constrained by this global anomaly. And standard model will enable phases. And dark photon, what Isabel talked about, also show up. Certain type. And last one is try to use symmetric mass generation, new mechanism to give mass to subs from CPU. Okay, so these are 3 messages. And then we will move into the light sector, the chiral sector. So indeed, there will be either 16 fermion if you count right neutrino here or not, 15. And there are 3 generations of them. And maybe some of them will be there for certain generations, but not the other. We don't know yet. And each of the disks will be 2 component spin 3-hop biofermion, all written in the Latin basis. And we will consider all the possible gauge group compatible with the algebra, the full version. And if we drop right on this and drop a quark and lepton, the guard, maybe you will yell at me and say, oh, fertility local anomalies are not cancer. You know this. So how about the non-fertility global anomaly? That could be equally important. So we should check. If right-hand neutrino does not exist, maybe we should try to find something else to replace it. And the mass may not be derived around the mass only, maybe something else. And we are really looking at the same STEM model to look at Young-Mills Maxwell term and possible CR term, and the biofermion Higgs term. Classically, there's a U1B and U1L very on lepton symmetry, but ADG anomaly fundamentally break. There's no this, only the U1B minus L or some discrete B plus L subgroup. Many guys actually break this discrete B plus L, but SM preserve that. And we can look into this more carefully and play a role. Photon will decays with this without this discrete B minus L protection, but with that you protect a single photon decay. CS current here also emphasize that in this work, and we compute additional possible anomaly constraint related to this discrete symmetry. And gather together the symmetry, we need to ask what's the space-time symmetry. The Lorentz group SO rotation rated by fermion parity will be a spin group. This will be a deformable and get gravitational background probe. Internal symmetry consists of U1B minus L discrete B plus L in internal symmetry. Once you gauge the continuous part of the internal gauge group, you will change this global symmetry to include additional higher symmetry. Charge object will be Wilson to whole line. And I won't go too detail for this because it doesn't play a role in my talk, but soon we'll talk about this tomorrow. And B minus L can be considered as only a discrete Z4 subgroup, as well as he did. And that's a good one because it preserves even more higher order 4N fermion interaction deformation. And this will be a combination of B minus L and hypertroph Y. And we will all the things on the table with 3 generations. And particularly the quantum number of U1, this X, and Z4 version of that should look at it carefully. All the quark and lepton carry charge 1. So the Z16 global anomaly for this one actually counting a number of quark and leptons. So the 15 and 16 will need to be matched. This anomaly due to that to cancel. And another thing is that there is actually 4 of a doublet, SO2 doublet, and 4 of SO3 triplets. It's actually highly related to once you compute the anomaly classification from coordinate group, there's a lot of Z4 and Z2. And this is actually related to a subtle calculation for this 4 doublet and 4 triplets, SO2 and SO3. And the outcome main message is that actually Z16 and Z2 anomaly will play some important role. And let me write it down specifically. Everything here follows mathematically, so whether you do BINO or not doesn't really matter. Even spin theory, pay attention. So the anomaly for fertility one with continuous U1 and U1 cube and U1 gravity square, there's actually 2 terms. This term is U1 cube and the other is U1 gravity square. It's the Feynman graph. And don't worry about this topological term in the back, but you look at the coefficient, whether it's energy or not, it relates to the number of generation biofermions minus NF, typically 3, the number of right neutrino. It will not vanish to 0 if the number does not cancel. And if you break the U1 B minus L down to discrete Z4, there's a Z16 anomaly. I think emphasized by Miguel at Harvard earlier. Also, this anomaly for particle physics. And there's another one include the spin 10 like granted by theory. For particular version of that, it can have a Z2 global anomaly in terms of stable Winnie clause. And all these 3 are mixed gauge gravitational anomaly, and these 2 are global in the sense of not captured by Feynman graph. We can also consider other more probe, but let's focus on this. So everything followed here is so mathematically sensible. And now we want to do something more rectilinear, and it's your taste where you want to agree with me. But the assumption I have just standard model, let's say with this gauge group and 15 observed biofermion times 3 generations, and this 3 B minus L might observe preserve at high energy. If we dynamically gauge if we assume that these are preserved dynamical gauge, we want to cancel that global anomaly. The only one does not vanish is the Z16 class. So if the right-hand neutrino does not match to the 3, there's a new hidden sectors. And this kind of logic is similar to some kind of predict low energy theory or some hidden sectors type of constraint, like Lipschitz multi type of statement in this matter. Standard law use the right-hand neutrino to cancel with the raw Mariana mass. But there are several possibilities. One possibility is the symmetric gap TQFT. Some people call topological ring short mechanism, boundary topological order of the bulk or some topological superconductor states. And this one is the one I'll mention a bit more. Another one, like a 5D extra bulk or interacting CFT, will be interesting. But main point is the high neutrino contains more than particle physics, but also this gap excitation of extend objects, 1D line, 2D surfaces, and also particle CFT. But these things I think also mentioned in the conference, but the difference is that those are constructed in order to cancel some anomaly. So then I can just construct by because a particular purpose to mesh. And if I want to draw a cartoon picture, the standard model, the paradigm we have confirmed in the textbook is something drawn here. And possibly there are some additional sectors of light surface. And these are cartoon. And these are 5D bulk with some topological invariant. And then one need to ask how to give the neutrino mass. I think if you want to ask, you can ask in the end. I'm not going to say this now. Okay, so let's go back. So we discussed a chiral sector. And there's a possibility of another brane on the other side is the mirror sectors, and this will be the dark sectors. And we'll pay attention to that from the part 3 of that message I want to give. But let's focus on this chiral sector for a moment. Again, we're looking to the phase diagram at 0 temperature, and where there are some parameters that we can tune. For example, the fermion mass from positive to negative mass, or to tune the gut Higgs potential to tune the quadratic coefficients. And this phase diagram shows that we want to put Georgi-Glashow and Pati-Salam in the 0 temperature phase diagram along with standard model. And there's a natural way to do this is include the spin 10 gauge groups SO10 dot theory. And earlier in the first part, I was trying to go between 15 and 16 biofermions to the enlarged model. But right now we are going to just focus on 16 fermion model. And this will require standard model gauge group to be MAZ 6. But the new thing here is that there's a possibility to have an underlying C2 class global gravitational anomaly, gauge gravitational anomaly that control the phase diagram. So all these 3 phases are meant to cancel that W2, W3 anomaly, while the SO10 alone break down to this can match the anomaly by breaking the SO10 symmetry don't solve. But SO10 alone cannot be matched. So one need to add additional sector, which is similar to this WZW terms in earlier people's work, except these are now discrete clause. Okay, some detail. So the phase diagram for that type of formation will look like this. It's like all the Georgi-Glashow, Pati-Salam standard model will be some phases around. This can be looked at some as a Landau-Ginzburg type of symmetry breaking phases. If you look at the gauge group as some internal symmetry group for a moment. And if you want to go from GG to PS, there's only just go through this point, very fine-tuned. And however, there's a possibility, other than the familiar model of SO10, if you consider the phase diagram are controlled by some underlying anomaly, which it looks like living on the boundaries of 5D bulk controlled by W2, W3, such a term, then the phases here are just matched by anomaly cancellations. And then we need to, other than aiding this Higgs got Higgs potential to have symmetry breaking down to these phases, we need to match this W3 anomaly by aiding the topological term. This term is related to some topological model you heard earlier. This can be computed by breakdown SO10 to U5 or the spin 6, spin 4, and compute the second cohomology or multiple group. You can actually write down such a term. And the physics layer is that the topological monopole in 4D extend to 5D bulk. They can have a wall sheet of 2D surfaces. If they're linked, you can compute the statistical phase. You can give plus or minus sign. If it's minus sign, this signatures the non-trivial anomaly underlying. And then the low energy physics from UV of this theory can flow to some IR. And we predict possibility to have something similar to a critical CFT region of deconfined quantum basis with U1 dot photon and some emergent partons like this. And certainly there could be other IR physics, but these are kind of taste how to build a model with some constraint. Okay, so let me go to the third part. Actually, where's the camera? That should
There is no cap.
Yeah. So the last one is that you know the CP theta angle, the CR3 bar consists the CR3 of the Yang-Mills FOHF and the angle plot between mass metrics, and this is known to be small, almost zero. It's a challenge for us because the left-hand quarks participate weak interaction for deliberate P and C, and CK matrix, the W boson interval with quarks give order 1 CP violating phases. So naive expect the CL3 bar should be order 1. And the chiral transformations can make that theta 3 and M invariant, but the combination will be physical. The typical solution is, for example, can be a massless quarks. And one of the determinant of the mass eigenvalue 0, so you can just have a slope to make the CR3 to be CR3 bar to be 0. These are probably a good solution. A mean field mass means that you have some target space mass field, and then you have some condensation like Higgs. And then small fluctuation around some theta of the Higgs condensate gives some Goldstone mode breaks continuous U1 symmetry or anomalous U1. And there will be some Goldstone or pseudo Goldstone. This will be pretty clean solution. However, there's another way to give gap, and these are known as more like disorder instead of order mass. The target space of a mass field can be disorder, and with certain conditions, you can still give a gap. And there's no mean field mass value. And if you are quick, you probably know how I'm going to solve the problem. In quantum matter, there's a famous superfluid to insulate the side of transitions. These are symmetric node phases. The low line mode is like superfluid mode. So the old solution is like solving problem in this side, superfluid side. So these are PQ and Goldstone potential. If you go to a phase transitions, and this can be continuous OPKD transition depending on dimensions, go to insulated sides, this can be still the gap phase. This have a low volume gap phase, this is gap. And this one way of solving this is that U quark may consist of mass fully from SMG, symmetric mass of this type. Other quarks may consist a portion of SMG, but dominantly from Higgs. And this will be one way, just using concept chiral sector of the same model. And because Isabel want to see how explicit interaction tend to keep the energy gap without the mean field. That's one example is a 0 plus 1D Bilowski Kitaf interaction to gap M Rana fermions preserve Z2 time reversal and fermion parity. This will be full complex fermion. Complex fermion is a two combination of 2 Marana. And this no mean field mass, but you can solve energy spectrum gap. Another one is the U1 symmetry model with funny number 345, 34 left moving, 50 right moving with some interaction term with multi-fermion. This is highly irrelevant in terms of RV sense, and you'll be very surprised this can drive the gapless phase. But this is not surprise to many of us familiar with that. We do a numeric social check, and we know the theoretical reason this can drive the phase from gapless to gapless just by this interaction term. And it requires no mean field mass. So there's a real two ways to rewrite. One is multi-fermion disorder scalar by field. It does not have a mean field value or condensate. It's a different value. And the last one is chiral SM. Rosama and David Tom give some smooth S confinement type of a way to do this. We find this difficult to implement to solve strong CP. There's a difficult complex mass matrix. However, we believe that a Platon Higgs type of a scalar field coupled quarks in a certain way introduce certain new set of quarks and leptons and requires some no mean field mass can solve strong CP. And this will be later maybe shown in the paper. And in the second possible solution involving SMG for strong CP is that we imagine there's a chiral sector and neural sectors. And they are related to each other by a fermion doubling, Nielsen-Newman fermion doubling. It's kind of related to parity solution, but still somehow different. The symmetry respect between the chiral and neural is by a parity, which left to right on the same sector, but also respect the combination of parity and reflection. Reflection is flip these two along the middle axis. And if you have that, this will impose the CR3 and on the chiral sector and CR3 prime on the middle sector combination will be 0. And the field stress on the two sides actually is the same one. And let me comment a few properties for this type of solution. Is that these are based on Nielsen-Newman fermion doubling based on UV. These are a problem for regular chiral fermion. But right now we use this property at UV. And these are relative domain more fermion in the lattice. And however, we want to gap this mirror fermion based on low energy. And that will break the parity symmetry related to some direct model. And however, the symmetry in gauge group does not necessarily need to be double. So that's a kind of different from the parity solution. and it will respect a parity reflection or combined symmetry. This symmetry actually would just be a pi rotation to flip the strip by pi, 180 rotations. And the Higgs mechanism is triggered on the chiral sector, while the symmetric mass is triggered on the mirror sectors. It's in contrast with the twin Higgs that both have used Higgs. And the physical combination of the theta term will be theta bar of this. And there will be a mass metric from MU and B from chiral and some SMG from the mirror. But importantly, SMG mass is not really a mean field mass. So this will be 0. And another crucial part of construction is anomaly-free condition on the chiral sector within the symmetry that you want to preserve and gauge will be important. And topological gapping condition, the way to design the interaction will constrained by this. I cannot emphasize the deep mathematical structure between the two, and I hope you will appreciate at some point. And using that, the Higgs condensate along the extra small extra dimension, it does not need to be large. It can be small. It can also be large. It does not matter. The Higgs condensate and SMG hopefully do not interfere. And the energy scale drawing by preserving parity reflection at high energy, and it will impose sub in the strong CP, and then we want to break the parity and condense either the SMG giving the gap on the mirror sectors and also the Higgs condense on the chiral sectors, and that's basically the idea. And low energy follow up on the same as the usual standard model physics. So produce the low energy standard model theory. So this is the rough idea. And let me summarize. I hope you get some message. In the usual way, thinking about mass is Anderson Higgs or explicit mass term is a symmetry breaking and require usually no topological order, spin field, and confinement. You hear the loud from the speakers, and it's also break chiral symmetry. And there's also S confinement. However, we are using a symmetric mass generation, which possibly can reduce to south from CP. And there's also a gap TQFT type of low energy theory with low line topological order that can be used to replace writing neutrinos. And there's also construction using extension instead of breaking, and possibly also using CFT to match. So we are kind of using power and using this method. So summary, neutrino might be replaced, as I said, to some highly interacting sectors, CFT or TQFT. And there is some quantum criticality similar to what the beyond Landau Ginsburg basis people pursuing condensed matter for deconfined DQC between granular theory and our new dark gauge sector, dark photon, CFT is low energy possible realization, and strong CP may be solved with symmetric mass with two types. One is just applied to the chiral sectors. Another is hypothesized another mirror sectors and gap the mirror by symmetry. Thank you very much.